and we're going to talk about Introduction to AC Electricity. The slides we're going to look at today are from the base math book by Singer, Foster, and Schultz. I think that's the last guy's name. We just refer to this book as Singer, as you know, and it's a great book on the math of doing anything, especially in electricity. And so, the generation of AC voltage wave, we've already talked about how that's created. We've talked about how a bunch of windings go past the magnetic field. We've talked about how voltage is induced into those windings by going past the magnetic field, and the greatest point of induction is at the top of the arc closest to the magnet when it's going directly across, and it drops to zero on its way up and its way back. So a lot of this is going to be review. But this talks about frequency because this book also talks to electronics people. Now, as you know, electrical equipment is becoming more and more solid state, and you need to understand electronics more and more as time goes by. In the past, if something in a PLC or some high-tech piece of equipment was bad, there was a card we could take the whole circuit that was giving us trouble out and get a replacement. But that meant that the equipment was going to be down until we got a new piece of new card. Well, now, well, always they've hated having the equipment down because that shuts down their money-making machine, and everybody hates that. Okay, so this stuff about frequency, it's electronic stuff. It's more oriented towards solid state stuff, but we need to start learning this stuff too. Okay? So it will come in handy in other places, and later, as time goes by, this will become more and more part of general electrical knowledge. Okay, so frequency of a radio wave, if its wavelength is 297 meters, what New York City station broadcasts at this frequency? How would I know? I'm not from New York. I don't know anybody. I know very few people from New York. Okay, so if you're going to take the FCC class, by the way, you might need to know this because finding the wavelength or finding the frequency of the station is something sometimes you have to do. And what you do is you always divide by 300,000. Or that's backwards. You take 300,000 and you divide by the thing you have, and it gives you the thing you're looking for. If you have the frequency in kilohertz, you divide by that number, and it gives you the wavelength. If you have the wavelength, you divide by that number, and you get the frequency in kilohertz. Okay, so the wavelength is 297 meters. So what is the frequency? And we know that the formula is the wavelength is 300,000 divided by frequency. So we can see that 300,000 divided by 297 is 1,010 kilohertz. Okay. That too. Instantaneous values, and this is something that we do need to know. You know that instantaneous values, as the voltage is being created, means something to us because, as you know, AC drops to zero 60 times a second. No, it drops 120 times a second to zero. Okay, it drops to zero 120 times a second. A full wave happens every 60th of a second, and it drops to zero twice in that wave, right? So it's twice 60, 120 times per second. Okay, if we have a current maximum of 100 milliamps at 70 degrees of the rotation of the generator, how much current is being made? So you can just take the sine of 70 degrees, which is 0.9397, and multiply that times 100, you get 93.97 milliamps. An AC voltage wave has its instantaneous value of 70 volts at 30 degrees. Find the maximum. Okay. Instantaneous is that point on the arc where you find the sine wave. So if it's at 30 degrees, what is the sine of 30 degrees? 0.5. So 70 divided by 0.5 is going to be about 140, I think. So what is that? What is 140? Peak. That's the peak, right? What's the RMS? 45 degrees is the RMS. Remember that square we built going up to 45 degrees and then 45 degrees up from the other side and then drawing a line across and filling hole that block in. That's the equivalent heat making ability of DC that AC is making, and it's called true RMS power. Okay, phase angle. The phase angle is that portion of rotation. An AC voltage wave has a maximum value of 155.5 volts. Find the phase angle at which the instantaneous voltage is 110 volts. So you know that the sine of something is equal to 110. So sine of theta times 110 is equal to 155.5. So 155.5 is the peak, right? So peak times that sine is going to be 110 volts. So what angle is that? So you got to kind of back into that by saying, what is the sine of this angle if 110 divided by 155 is its sine? Because that's, what is sine? Oh, hell, it's the side opposite over the hypotenuse, right? And we can see that that's a fraction here, 110 over 155.5. And that sine is 0.7074. In other words, the RMS point, right? Okay, an AC voltage wave has an effective value of 110 volts. Find the maximum value if the instantaneous value at V is 40 degrees. Instantaneous angle, in other words, is 40 degrees. So we need to find the sine of 40 degrees, which is about, I'm confused by this. Oh, there we go. The sine of 40 degrees is 0.6427 times 155 will give us, we don't know yet. Oh, wait a minute. Is that the same one? Let's see. There we go. 99.6, that's right. 155 times 0.6428, which is the sine of 40 degrees. And only we have 1.414 times 110 is equal to 155. Well, that's getting our maximum voltage. Okay. Our peak voltage. Okay, and we have a couple of problems here. This is not really the area I want to discuss a great deal. Go ahead and look this over later, but I think we're going to start skipping forward. Let's see, find the frequency of a signal whose period is 4 seconds. I really don't want to do that. So I don't want to do that here in class anyway. Let's look at the problem though. So you can take a look at this and stop the video and figure out what's going on here. So you can do the period calculations. Time-based, yeah, another problem. I don't really want to get into that right now, so we'll just show them in the slideshow. And you can look those over later. Now, vectors and phasors are what we're talking about yesterday. Or at least the ones that are related to a circuit. So if we have how is that in vectors and phasors? 22 ohm electric iron has operated from 110 volt 60 cycle line. Draw a phasor diagram and find the current and power used by the iron. All right, we can find all that stuff. That's not a big deal. But finding the phasor, again, they're going to use, I've told you this before, I'm going to tell you again that we're not going to do it this way. They're using the Pythagorean theorem. And why do we not use the Pythagorean theorem? Because it leaves you not knowing the angle. We need to know the angle because we're always going to move forward and do another triangle from that with that angle. Okay, so this is very nice. This is doing it with a Pythagorean theorem. We're not going to do it that way. Okay. It's all very nice. Not an example of what I want to talk about. Okay. So I'm going to stop this and we're going to go into the free form again, as it were. Let me hit pause for a second while I get set up. One more time. Okay, so we've got a triangle, and we've got a couple of things here to remind you, like sine, cosine, tangent is oh hell, another hour of agony, and that the PEIR or PEIZ will help you remember to, if you're going down, divide, if you're going up, multiply. And so it's kind of a trick to help you remember certain things. So let's look at this circuit we have, and it's got 240 volts. It's got a total resistance. Now this is some kind of winding, like a motor, a coil of a transformer or something, some kind of inductor, and it has a total DC resistance of 24 ohms, and it's got an inductive reactance of 12 ohms. So we want to know a couple things. Like first we want to know what is our impedance, because we know we've got a 240 volt supply, so we know that we're going to have a certain current. We kind of like to know what the current inflow is going to be, right? So let's look at this. Now, if we what function do we have right now? We have the tangent. And so let's look at this. And the tangent is what? What is the tangent in this case? The opposite is the 12. So the tangent is equal to 12 over 24. Literally, that fraction, 12 over 24, is the tangent of that angle. So we want to know the angle, right? So we're going to take our handy dandy TI-30X2S and we're going to turn it on. We're going to hit clear a couple times, and then we're going to go second function tangent, and that means tell me what angle has this tangent. And then we're going to put in 12 divided by 24, and the angle is 26.565 degrees. Okay, now what I want to do with that information is I want to find the z. Now the z is the hypotenuse, and I can use either the cosine or the sine, but I like the cosine, so we're going to take the cosine of this angle. We're not going to touch anything on the calculator except cosine, second function, answer. In other words, find the cosine of that degree that I just found a minute ago, and it tells me that the cosine of this angle is 0.8944. So the cosine of 26.5650 degrees is equal to 0.8944, and so on. So it's a long number, and it's all in my calculator. And if I just use these first four numbers, I'll be okay, I'll be close. But if I use the whole number by not erasing this number out of my calculator, I can use the whole number. So if I know that the cosine is this long number, I might want to look at what that means. Let's look at this, and that is equal to A over H. And we're looking for H, so we have A is 24, and it's over the hypotenuse. Now, I've said this before, I'm going to say it again, probably a couple times, that in algebra we can exchange these two numbers, or these two symbols, directly, and it's still the same formula. So we're going to say that H is equal to 24 divided by 0.8944. Now we have the variable on the left all by itself, and we have numbers all on the right. So now we have 0.89 in our calculator and all that long number. So what we're going to do is we're going to punch in 24 divided by, the last answer I found is second function answer, hit enter, and I get 26.8328. And that's this right here. This is 26.83 ohms. And if now we want to plug that in here, right? 26.83. And we'd kind of like to use that whole long number still, wouldn't we? So we could find the current. We could put in, well, again, we're not going to hit erase or anything like that. We're just going to start doing what we want to do. 240 divided by, what did we find last? We found the impedance last, so we're going to divide by that. Second function answer, enter, and I find that the current is going to be 8.944 amps. Okay, so now we could find our power, couldn't we? What do I have in my calculator? 8.944, and I've got a really long number. I want to keep that number, don't I? But I want to find my total. What kind of power is this? This is apparent power. What's coming into the circuit? So let's multiply that 8.944,27191. In other words, the whole long number without, and I'm just going to multiply times 240, and I'm going to get 2146.62. And that's VAs, right? So that's VAs. Now, let's go to the next triangle. It won't let me go to the next thing and hang on to my, I don't care. I don't care. Clear the ink, close ink, I don't care what you do, but do something. No, not that. Anything but that. Okay, let me hit pause for a second. All right, back to our problem. We had, now we want to get rid of the resistance and the impedance and the X sub L. We're going to get rid of those. We're doing a new thing. We're going to have power, apparent power. Down here we're going to have power. We're going to have true power down here. And over here we're going to have reactive power. Okay. Now, we have our total power is 2,146.625 VAs, right? That's our total apparent power. That's our hypotenuse. Still my calculator, right? Okay. Does this angle have the same angle as my previous angle? Of course it does. What was that angle? .565 what? 26.56. Huh? We didn't have another number? Okay. Okay, 6.2. I'm going to leave that. I'm going to clear my calculator. I'm going to hit second function tangent 12 divided by 24. 5650. Okay, 5650. Okay. Oops. Okay, what happened there? Hang on one. Okay, so we're looking at our second triangle based on the first triangle. And the first triangle told us that the phase angle for this circuit is 26.5650 degrees. So if we want to move over to the power triangle, we can do that. And we've calculated that we have 2146.625 VAs. And that's our hypotenuse up here. So we're going to put in our 2146.625 VAs. And we want to know what our true power is. How much real power is this circuit going to generate? So we want to go back, and we found the cosine of this angle before, didn't we? The cosine of the angle is 0.89442791 and on and on and on. And if we took the angle of 26.5650 and we took the cosine of that, we'd get that number, 0.8944279191. And so we're going to assume that that is the cosine of the angle, and it is. And what is the cosine? The cosine is the A over the H. And we know one of those already. We know the hypotenuse this time. So our cosine is 0.89 and so on. And that's equal to A, which we don't know. That's what we're looking for, right? Over H, the hypotenuse, 2146.625. And now you can see that if we just multiply both sides by 2146.625, we'll wind up with if we multiply A over 2146 times 2146, the 2146 will drop out of the right side, and the left side will be 0.8944, and all that long number times 2146.625, and that'll give us A. So I'm going to multiply. I've got 89.4427 in my calculator. I'm going to multiply that times 2146.625. I'm going to find that it's 1919.99999. So we're going to round that just a little bit. How about 1920? 1920 watts. If I just add 1/1000th of a watt, we can round up to 1920, right? So 1920 watts. So this circuit is going to take in 2146.625, 2146 and an eighth. And we're going to find, no, that's not an eighth. Sorry, forget that. We're going to find that it only produces less than 2,000 watts. Okay? Now, another thing we might want to know is how many VARs is that going to be creating? And we would use the sine to find that. So we need to go back to our angle, and I'm going to divide by 2146.625, and it's going to take me back to my cosine. So I go back to my cosine, and I'm going to say second function cosine, second function answer. That won't work, will it? Yep, 26.56 degrees. Now, I've got my angle back in my calculator. You'll probably have to listen to that a couple times to figure out what I just did. That's okay, though. So now I'm going to take the sine of this angle. Or I could just take the sine of 26.5650, right? That's still accurate enough. So sine, second function answer, gives me the sine of this angle is 0.4472. Well, let's put that down. The sine is and a bunch of numbers behind that. So we know that the sine, 0.4472, is equal to O over H. Do we know one of those? We know the hypotenuse, don't we? So if we multiply both sides by the 2146.625, we'll get 0.4472, which is in my calculator right now, times 2146.625 is equal to O, because if we multiply O over 2146 times 2146, the 2146 is A over A and drops out to be 1. So now I'm going to multiply this times 2146.625, and I get 959.9999, and that we're going to put that in over here. And that's VARs. We could round that to 960, couldn't we? Whoops. I know what I did. Uh-oh. Well, I just dropped everything out. Okay. Well, I don't know how I did that. I am awfully clever, don't you think? Okay, so anyway, I wind up with 960 VARs. Now, the point of all this is that if we know the number of VARs for the future projects, we can figure out how to get rid of them. Okay? If we know the number of ohms of X sub L, we can figure out how to get rid of them. But that's in a next step. So these are the steps you need to know how to do now. So you might want to watch this and do this with another couple of problems, because we're almost out of time for today. Yes, sir. Okay, so the question was, how did we find out our original angle? We knew that we have the tangent function because we've got the O and the H. O is opposite, A is adjacent. This is the opposite. Whoops. This is the opposite, and this is the adjacent. So the tangent is 12 divided by 24. So if that's true, what angle is it? So we go second function tangent, 12 divided by 24, enter. And it'll tell you that we have 56 point whatever degrees, or 26 degrees. Right? Okay. When we used cosine before, it was because we were going to the next function, or the next item we wanted to find. We're looking at the cosine is because we had discovered our angle. So if we have the angle, we have any one of these, because we can take the sine, cosine, or tangent of any one of those angles, and it gives us a number, right? So we have a number, and if we want to find something, and we know the cosine of the angle, and we know either the adjacent or the hypotenuse, we can plug that in and find out the one we don't have. Well, in this function, we found the angle, and we're looking for the impedance, right? That is the hypotenuse. So if we're looking for the hypotenuse and we happen to know this, and we know this, we can take the cosine that we know, plug in the adjacent that we know, and then switch these two places in location, and we wind up with H is equal to the adjacent divided by the cosine of the angle, which is what we did. And that told us what the hypotenuse was.